Hi, today's lesson is on logic gates. You've already done a little bit of this with Mr. Baker's videos, but I want to do an extension of that work, just going into a little bit more detail. So let's have a look at our lesson objectives. So by the end of today's lesson, you should be able to recall the symbols for each of the logic gates. You should be able to recall the function of each logic gate and recall its truth table. And you should be able to work out the output of several logic gates placed in combination. So it's this last point here which is going to be new to you. So I'm going to start by recapping the logic gates that you've already covered in a previous lesson. So you should know that this symbol represents a NOT gate. It's really important you recognise these. You will not necessarily be given the name of each, and you may have to actually answer questions in a paper that ask you to name each gate. Really important that you also need to be able to recognise the truth table. So here it's a very simple truth table because we only have a single input. Now, obviously, when you've got a single input, there's only two options. That is either an input of a 1 or an input of a 0. And what a NOT gate does is it reverses that input. So our 1 becomes a 0 and our 0 becomes a 1. Nice and easy one to start with. The second logic gate here is an AND gate. Again, it's really important you recognise this symbol. It has a flat edge on the back here and then a curved front here. Okay, so make sure that you can both recognize and also draw that symbol. Again, let's have a look at the truth table. Now here we actually have two inputs, which I've labeled input A and input B. Now, the thing here is you've got to be logical in terms of working out the various combinations of inputs. And the way I always do it, I always start with 0, 0, then do 0, 1, 1, 0, and 1, 1. You could do this in various different ways. I know Mr. Baker likes to think about this as binary. So those of you that are doing computer science will recognize that those numbers, 0, 0 is obviously 0, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. And then just keep going up as you go. Now, what does an AND gate actually do? In order to get a positive output, or 1 for your output, both inputs A and B have to be 1s. So therefore, when we've got a 0 and a 0, we get a 0. A 0 and a 1, we get a 0. A 1 and a 0, we get a 0. And a 1 and a 1, we get a 1. So again, very important that you remember this truth table for this gate. Okay, now this one is slightly different in terms of its shape. So here at the back end, we've got a curve, and here we have a pointy front to this. And this gate is what we call an OR gate. Now, again, with the truth table, we need to be able to remember these inputs. So again, it doesn't matter how you do it, whether you just do it methodically or whether you do it using binary. But here we've got 0, 0, 0, 1, 1, 0, and 1, 1. Now, what does an OR gate do? With an OR gate, either input A or input B has to be a 1 in order to get an output of a 1. So with 0, 0, we get a 0. With 0, 1, we get a 1. With 1, 0, we get a 1. And 1, 1, we get a 1. There is another gate called an exclusively OR that isn't on our course, in which case that final row would actually be a 0, but you don't need to worry about that. When we're saying input A or input B, that also includes when both of them are 1s, as you can see from this truth table. Okay, so now we've got two more here. So this is the AND symbol, but it has this little circle on the front in the same way that the NOT gate does. So effectively what this is, it's a combination of an AND gate and a NOT gate, giving us a NAND gate. Let's look at the truth table. Again, with the inputs, it's the same as last time, 0, 0, 0, 1, 1, 0, and 1, 1. Now, what I often find it easy to do here, or to help me remember how this happens, or how this works, I put another column, not necessarily labelled, that tells me what an AND gate is. So with an AND gate, it would be 0, 0, 0, 1. So then, in order to fill out the actual truth table, I'm going to reverse those options, because remember, an NAND gate is a combination of an AND and a NOT. So we therefore get 1, 1, 1, 0. And obviously, I don't need that outside column there. It was just for my workings. I think it just helps to actually think about what an AND gate is in order to fill out the NAND truth table. So here we have the OR gate symbol, but we also have this dot or circle on the front of it, which indicates to us that it's a combination of both an OR gate and a NOT gate, giving us a NOR gate. The truth table inputs are exactly the same, so 0, 0, 0, 1, 1, 0, and 1, 1. And again, whenever I'm doing something like this, I always like to write down the output of an ordinary OR gate. So that would be 0, 1, 1, 1. And now I can just reverse those outputs to give me the output of the NOR gate. So we're going to get 1, 0, 0, 0. And like I say, that column outside the table isn't actually needed. It's just there for my workings to help me remember what these outputs are going to be. So that is all of the different logic gates you need to be able to recall. And all their truth tables. Please make sure that you maybe do a revision card or a poster, something that is going to help you revise that at some point in the future. Hopefully you've got all these into your notes now at some point, but like I say, it would be quite good if you can collate them all into a single document so that you can then revise from those at a later date. So moving on to the main focus of our lesson, which is combining logic gates. You'll see here I have a schematic that contains two logic gates, and the first thing you're going to notice is that neither of those gates is labelled, and they won't be in an IGCSE paper. So you need to recall that this is a NOT gate and that this is an AND gate. If you don't recognise these symbols, you're not going to be able to answer these questions. Now, when I'm building our truth table, it sometimes helps to add additional labels. So I'm going to put an extra label of Q after the NOT gate and before the NAND gate. And you'll see why I do that in a second. So let's now look at our truth table. So I've now got input A, input B, and I've got this additional label of Q. So the first thing I'm going to do is I'm going to actually populate my input in A and input B. So that's the same as it has been in the past, 0, 0, 0, 1, 1, 0, and 1, 1. Now in order to do the next column, all I need to do is look at this NOT gate. Okay, so I'm going to be focusing on input B, and so I'm going to be focusing on this column here. And what does my NOT gate do? It reverses that input. So my 0 becomes a 1, my 1 becomes a 0, my 0 becomes a 1, and my 1 becomes a 0. So I've now populated that column entitled Q. Now what I want to do is I want to have a look at the AND gate. Now with the AND gate, I've got an input A and I've got Q going into it. So when I want to complete my final column, the two columns I need to be looking at are input A and Q. So I can ignore input B now, that's done with. I'm just going to focus on these two columns. Now if we look at that top row, it's a 0 and a 1, and with an AND gate, that's going to give us an output of a 0. The next column row down is a 0 and a 0, so that's going to give me a 0. The third column is a 1 and a 1, so that's going to give me a 1. And the final is a 1 and a 0, which is going to give me a 0. So I've now completed my truth table for these this combination of logic gates. Okay, so a slightly more complex one here. Again, very, very important we recognize these symbols. Just to recap, this is a NOT gate, this is an OR gate, and this is an AND gate. So again, I'm going to add some labels. Now, if you think about this, we're going to actually have two additional labels here. So I'm going to add a P and a Q. So I've got my P after my OR gate and before my AND gate, and I've got my Q after my NOT gate but before the AND gate. The other thing that's new here is I've got three inputs. So with my truth table, I've got input A, input B, input C, P, Q, and my output. Now, because I've got three inputs, this becomes more complicated. And again, there's different ways you can do this, but I would just suggest that you be very logical about the way you fill it out. You can use this trick of using binary if you happen to know how binary works, but it's not how I do it. I know that's how Mr. Baker does it. I just do it logically. So what I do is start with 0, 0, 0, then I do 0, 0, 1, 0, 1, 0, 1, 0, 0. So that's the 3 that it has a single output of a input of a 1. I then go 0, 1, 1, 1, 0, 1, 1, 1, 0. So they're the different combinations of having 2 inputs of a 1. And then finally, we've got 1, 1, 1. So it doesn't really matter how you populate those inputs, but I would suggest you're logical about it. But whatever you're happy with, just try and make sure that you've got every single possible combination of those inputs. Okay, so now we're going to focus on this column P. Now, if you think about column P, that is dependent on both input A and input B. So I'm looking at these 2 columns here, input A and input B, and this is an OR gate. So let's go down and look at each of those combinations for input A and input B. So we've got 0 and 0 is going to give me a 0. Again, 0 and 0 is going to give me a 0. I've then got 0 and 1, which would be 1, 1 and 0, which would be 1, 0 and 1, which would be 1, 1 and 0, which would be 1, 1 and 1, which would be 1, and 1 and 1, which would be 1. So I mean, once you've got to this stage, I'm hoping it's relatively straightforward. I hope you can see where that column has come from. We now need to have a look at column Q. Well, this Q is literally just the reverse of input C. So now, in order to populate this column Q, I need to look at this column input C. And I'm literally just going to reverse it. So my 0 becomes a 1, my 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, and 1 becomes a 0. So again, relatively straightforward once we've actually worked out how that NOT gate reverses that input C. Now, in order to do my output, this final column, I have inputs of P and Q. So I'm actually now going to be looking at these 2 columns when I'm populating that final output column. And this is an AND gate. So let's go through and finish this off. A 0 and a 1 is going to give me a 0. A 0 and a 0 is going to give me a 0. A 1 and a 1 gives me a 1. A 1 and a 1 gives me a 1. A 1 and a 0 gives me a 0. A 1 and a 0 gives me a 0. A 1 and a 1 gives me a 1. And a 1 and a 0 gives me a 0. So we've now finalized our table by completing that final output column. Now, I know as I'm reading through that, it just sounds like lots of 1s and 0s, but I'm hoping you followed through the logic, pardon the pun, of how I've got to those numbers. If you need to, just go back and watch that again to see if it makes any more sense. If not, drop me an email, send me a message on Teams, and I'll see what I can to help. Again, you could always come along to the Thursday morning drop-ins that we can chat about it. Okay, so combined logic gates, what is the point? I often get this, is why on earth are we doing this? What's the point in it? Well, actually, these things are incredibly important. Nearly every single electrical device you could possibly think of works using combinations of logic gates to make the decisions that it makes. It's not actually making physical decisions like a sentient being, but it is having to make decisions based on the various inputs that can affect the circuitry in order to determine what the outputs are going to be. I mean, even down to the microprocessor in your computer, that's what it is. It is a series of logic gates that are making lots of different decisions as to what each pixel on your screen is going to be doing. I mean, obviously, we're not going to be going into anything anywhere near as that complex, but we could potentially get questions that ask us to think about it in this way. So let's have a look at one of those now. So here, design a system that will turn the light on when the on-off switch is on and it is dark, or the test switch is operated. Okay, so we're going to break this down. Now, there's a couple of ways you could think about this. It says the on-off switch is on, and now I'm then going to put a bracket here to help understand how I intended this question to be read. And it is dark, or the test switches are operated. So the overriding thing is this on-off switch. Regardless of what happens, this is only going to work if the on-off switch is on. But then also there's going to be something else that has to trigger this light turning on. And that is either the environment in which you're in is dark, or I have pressed this switch so I can test to make sure that light is on. This might be a situation where you've got a kind of a security light, but in the day, somebody's in the building, they want to test to make sure that security light is still working. They want to press a button, see that it's come on, and then they're happy that it's operating. So how are we going to do this? Well, let's start by this whole process concept of it being dark. Okay, well, I'm therefore going to use some kind of light sensor. Now, with a light sensor, chances are when it's light, I'm going to get an output of a 1, and when it's dark, so if I like to write that down actually, light 1, dark 0. Well, that's no good to me because I want this to have a positive output when it is dark. So what do I have to do? I need to have a NOT gate, because that's going to then make sure that when it's dark, I get an output of a 1. So that's the first thing that I need to include in my circuit. Okay, so then I've also got this statement of or the test switch is operated. So I'm going to need a test switch and I'm going to need an OR gate. So now what this section of this circuit is going to do is it's going to give me this positive output if either the light sensor is dark or the test switch is pressed on. And then the final thing is to say, well, I need this output to be a 1 and I need the on-off switch to be operated. So this circuit that I've now created answers that initial question. Now look, I'll be perfectly honest, I haven't seen a question like this in a IGCSE paper ever. Normally it's asking you to fill out truth tables or to identify the symbols. But I think it is something that could potentially come up, so I think it is something. I doubt it would be this complicated. I think it would be a lot more simple, but there's no point in us giving you really easy questions. Because then if they did ask you a slightly more complex one, you'd be lost. So it's best that we kind of give you questions like this that do require a little bit of higher level thinking, so that when you get into an IGCSE paper, you find all those questions really easy. Now, what we're now going to do, and actually what I would like you to do for this one, is to actually create yourself a truth table for this. I'm going to help you by labeling the point after the NOT gate as P and the point after the OR gate as Q. So if you pause the video now, go ahead and create a truth table for this circuit. And once you're done, unpause the video and you can see if you're right on the next slide. Okay, so I've got a very small version of our schematic on the left-hand side here so that we can still refer to it whilst we're filling out our truth table. We have 3 inputs, on-off switch, test switch, and the light sensor. As we have with the other 3 inputs systems, we need to fill out all those various different combinations. So we've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Like I say, whichever method you feel more comfortable with filling out that combination of 3 different inputs, but just make sure you're methodical about it. Okay, let's now have a look at P. Well, it's very, very small here, but we should be able to see all P is the reverse of the light sensor. So here is my light sensor column. All I'm going to do for column P is just to reverse it. So 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, and 1 becomes a 0. So nice and straightforward. Okay, now with Q, I'm looking at this test switch. So I've got my test switch here and I'm looking at P. So I'm now going to be looking at this column here and I'm going to be looking at this column here. And obviously this is going through an OR gate. So if I look at these 2 columns, I can then populate Q. So we've got a 0 and a 1 gives us a 1. A 0 and a 0 gives us a 0. A 1 and a 1 gives us a 1. A 0 and a 1 gives us a 1. A 1 and a 0 gives us a 1. A 0 and a 0 gives us a 0. A 1 and a 1 gives us a 1. And a 1 and a 0 gives us a 1. So that's our next column completed. And the final column, our light, is dependent on both the on-off switch and Q, and it's an AND gate. So the 2 kind of columns I need to be referring to here are the on-off switch and column Q. And like I say, this is an AND gate. So let's go through and do this. So we've got a 0 and a 1 is going to give us a 0. A 0 and a 0 is going to give us a 0. A 0 and a 1 is going to give us a 0. A 1 and a 1 gives us a 1. A 0 and a 1 gives us a 0. A 1 and a 0 gives us a 0. A 1 and a 1 gives us a 1. And a 1 and a 1 gives us a 1. So I'm hoping you got that truth table on your own just by going through the process. If you were unable to do that, like I say, please do go back, have a look at the video again, and you can always contact me or come along to the Thursday morning Zoom drop-in session and we can have a chat about it. Okay guys, so a summary of what we've done in this lesson. So to start with, I recapped all of the different logic gate symbols and all of their truth tables. So you should be able to recall both of those two things, both the symbols and their truth tables. Now obviously the truth table tells you what the function of that logic gate is. And we've also looked at combining logic gates so that we have to look at multiple inputs and work out what the final output will be. And I think the trick here, and the really important thing I want you to remember for this, is be logical when you're working out the various input combinations, but also use those secondary labels, so the P's and the Q's that I was adding in, so that you can break it down into smaller sections. It's so much easier to do it that way than just try and look at the whole thing at once and work out every single combination. So break it down into smaller chunks. You might not have extra columns in the table that they give you, but you can always write them in the margin of the test paper. Okay guys, so like I say, have a look through this, make sure you understand everything. If you don't, send me a message or drop into the Thursday morning session, and I will put some more work up, probably some questions for you next week. See you later, bye bye.